and this graph denotes prism which has angle of minimum deviation, and again at the angle of minimum deviation, the important aspect which we need to do or the important aspect which we need to understand here is, at the angle of minimum deviation, angle of incidence will be equal to angle of emergence. So, this is important, and in this way they will ask what are all the devices which we use to convert a plane wavefront to a spherical wavefront. So, one idea is convex lens. So, obviously a convex lens converts plane wavefront to spherical wavefront, and a concave mirror also, that again helps in converting from a plane wavefront to a spherical wavefront. Whereas, if you observe a prism, this does not have any spherical parts. So, in a prism the plane wavefront will still, even after the output, it will still be a plane wavefront, only thing it is deviated. So, originally it was straight like this, but now after passing through the prism it is bent. So, going forward it will be like this. And again the incident plane wavefront, after passing through the prism it has become a spherical wavefront. So, again it will meet at this point, that point is called focus. In this also, this is the plane wavefront, and after getting reflected in this, it is converted into a spherical wavefront, and this spherical wavefront converges at this point. This is the focus, and this is Young's double slit experiment. In this experiment, all the fringes have equal intensity. So, it is like this. So, everything is equal. Okay. And now this is single slit. We obviously know that the central maxima, in questions they will ask what is the value of the size of the central maxima, that is not directly given in book. So, this value up to here, it is lambda by A, where lambda is the wavelength and A is the slit width of the single slit. Now, this is lambda by A and this side is minus lambda by A. So, the total is 2 lambda by A. So, just keep it in mind, if they ask you what is the total angular width of the central maxima in a single slit experiment, the answer is 2 lambda by A. And you can also observe the intensity reduces as we go further in a single slit experiment. And though this is not exactly a graph, this is important. Many students make mistakes, that is why I included this diagram in the presentation. So, here if we observe, the incident light is unpolarized. The unpolarized light is indicated by two things. One, if you observe the dots here and the lines here, the dot as well as line. So, this represents an unpolarized light, whereas this dot represents polarized wave. I hope you understand. The incident which is unpolarized now is converted after reflection, it becomes a polarized wave. And this graph is pretty easy. Once the threshold, so this is dual nature, once if the incoming is more than the frequency of the incoming light is more than the threshold frequency, then photoelectric current will come. In this case, after a certain stage, if we increase the intensity, the photoelectric current also will increase. This shows if the light have same frequency but different intensity, it does not matter how much their intensity value is, but they all stop at the same point. So, the stopping potential is determined by the frequency and not by the intensity. But if you observe the saturation current, so after a stage depends on the intensity, the saturation current depends on the intensity. If the intensity is more, then the saturation current also will be more. This graph same intensity but different frequency. So, same intensity refers to same saturation current here, but different intensity refers to different stopping potential. So, those values depends on the frequency. So, if the frequency is high, then the corresponding stopping potential also will be high. If the frequency is less or low, the corresponding stopping potential value also will be very less. So, just to check the understanding, let us say, just to check the understanding, we will do this. There are 3 waves, wave 1, wave 2 and wave 3. Okay. So, 1, 2, 3. So, since wave 1 and wave 2 have same stopping potential, their frequencies are same. Since wave 1 and wave 3 have same saturation current, their intensities are same. I hope this is clear. Okay. So, since 1 and 2 have the same stopping potential, so stopping potential is determined by the frequency. So, 1 and 2 have the same frequency, but they have different intensity. So, 2 has a higher intensity because the saturation current of 2 is higher, and 2 and 3, sorry, earlier I said 1 and 3, it is basically 2 and 3 because only 2 and 3 meets, they have the same saturation current, meaning they have the same intensity. And this one is plotting Einstein's photoelectric equation. We know the equation value is h nu is equal to h nu naught plus half mv square or ev naught. So, we will take h nu is equal to, so I will do this question, this is very important. So, h nu is equal to h mu naught plus E V naught, where V naught is the stopping potential, this is the threshold frequency, and this is the frequency of incident wavelength. So, incident frequency, threshold frequency, stopping potential. Now, in this graph we have plotted against stopping potential versus frequency. So, this will act as the y axis and this will act as the x axis. Now, by rearranging, what do I get? I get E V naught is equal to h nu minus h nu naught, and this E will go to the other side. So, it will become h by E nu is equal to h by this value. Now, if you observe, the slope y is equal to mx plus c. This is the general equation of a straight line. Now, this value is y, the stopping potential is y, and this is frequency, the threshold frequency, this is frequency, this is threshold frequency, this is nu, and the slope value is h by E. So, in case if we have to interpret the equation of the straight line in this graph, then the slope will give us h by E. So, any questions, the slope will be given by h by E. And this is alpha scattering. The important aspect which we need to know in this graph, it is not linear, it is a logarithmic graph. If you observe here, it is 10 power 2, 10 power 3. So, it is not 10, it is 10, 100,000, it is logarithmic scale on the y axis. So, here at 10 power 7, almost so much is, the scattering angle is 0 to 20 for so many values. And if you observe the scattering angle between 160 and 200, the value is very, very less. So, we should keep it in mind. This value here is logarithmic in the y axis for alpha particle scattering. And this is nuclei chapter. Here this is a graph between binding energy per nucleon versus mass number. Initially it is very small. So, if you observe these values, it is small. Then from 30 to 170 it is almost flat, and then the value falls. So, there are 3 regions basically. So, nuclear fission is the process from here to here. Okay. So, the binding energy of the reactants, the total binding energy of the reactants should be less than the total binding energy of the products for nuclear fission to happen. Similarly, for nuclear fusion also to happen, the total binding energy of the reactants should be less than the total binding energy of the products. So, the total binding energy of the reactants, there is again the values are very less here. So, the products, the total binding energy of the products in fusion, fusion means nuclei which has low binding energy, they fuse together to form nuclei which have high binding energy per nucleon. So, this graph is very important, you at least should know how it is. So, you should draw here it is constant and then it drops, and you need not remember all the values here, but you should write at least the x axis and y axis values, and you should mention that the binding energy per nucleon is in terms of mega electron volts. That is also important. And many students make mistakes in this graph. This is not a very popular graph or something, but what they do, they in general assume that this value is 0. Okay, usually that is what we assume, right? But in this graph, if you see, this value is 0, below that it is minus, and above that it is positive. So, this value is important. So, this graph, the shape of this graph, so it comes like this, it drops and then practically. So, this region is important for us, how it is, because that is where the potential energy is negative. So, when the potential energy is negative, it means that it is stable. Okay. So, a system is said to be stable when the negative potential energy is negative. So, what is the connection? So, we have seen that minus mb cos theta as the potential energy for magnetic dipole, and minus p cos theta for electric dipole potential energy. So, in those cases also, if the total potential energy is negative, it means it is a stable system. If the total potential energy is positive, it means it is a unstable system. So, in this case, the potential energy will be negative is the most desirable scenario. So, that will happen in this particular range. So, we know that nuclear force is short ranged forces. So, after that it gradually reduces to 0. So, it lasts only for a few FM values. This value denotes 10 power minus 15 meters. So, it is 1 into 10 power minus 15, 2 into 10 power minus 15, that is very small values. And again a very important graph, this has been asked several times in boards. We should know that the topmost point is n naught and the next one is t half. Okay. At t half, the total number just cuts into half, and again at 2 t half. So, this value is linear, but we have to again cut every value in half. So, this is n naught by 2 and this is n naught by 4, just half of it, and thrice or 3 times half lifetime, once 3 cycles have passed, it will become n naught by 8. So, when 4 times passed, when 4 cycles of half life cycle pass, the value will become 16 times, or I mean 1 by 16 times. So, it will keep on reducing by half. This is also an important graph. This is again not a graph, but this is very important. In this, we are seeing how the conduction band and valence band behaves for conductors, insulators and semiconductors. In conductors, the conduction band will have some electrons and the valence band will have some electrons. This is one type. The other type, both conduction and valence both overlap. So, this is the region of overlapping. So, this is also a possible scenario. And in insulators, the energy gap between conduction and valence is greater than 3 electron volts, and in semiconductors this value is less than 3 electron volts. And forward and reverse bias, this is important. So, how do we do? In forward bias, the current will be in the order of milliamps, and in reverse bias, the current will be in the order of microamps. So, just note it, this is milliamps and this is microamps, and this value is very small, and the breakdown happens at a very large value, and until then it is very small, and then after the current rapidly increases. So, this is how forward bias and reverse bias of a p-n junction diode works. And a half-wave rectifier, the input of a half-wave rectifier is like this. The half-wave rectifier is 1 full cycle, 2 full cycles, this is the input, and the output voltage is also this. This is an AC ripple, this is blank, AC ripple blank. Now, questions will be asked, if the frequency of a the input frequency of a half-wave rectifier is 50 hertz, what is the output frequency? The output frequency is also same. Now, if you observe, in the input there are 2 waves, and in the output also there are 2. So, it is basically the same. But in the case of a full wave rectifier, this is so this is 1 and this is 2, but however, if you see the output 1, 2, 3, 4. So, if the input frequency is 2, then the output frequency is 4 in this case. I mean, let us say this is for every 2 waves, if the the input is 50 hertz, then the output will be 100 hertz in case of a full wave rectifier. And this is a filter. A filter just the primary role of a filter is to make AC ripples into pure DC voltage. So, if you observe, though it is not exactly pure, you can observe then whenever the current falls here, it is actually supposed to fall here also in the output, right, but this output is given by a capacitor which is here. This capacitor actually charges in the first cycle, and when the current actually drops here, the capacitor gives output and it gives a constant output. Again, in the second cycle the capacitor charges, and again when the current is supposed to drop, the capacitor output is, the capacitor discharges and ensures a constant output DC. This is the filter. And a Zener diode, we just need to keep in mind, a Zener diode always works in reverse bias. That is why the reverse bias is drawn, and the Zener diode is different from a diode by this. So, if you could see the indication, that is different for a Zener diode. And a photodiode, it functions under reverse bias, and in a photodiode they will ask you a question, why it functions under reverse bias, why not under forward bias. The reason is the current in photoelectric, the photoelectric current will be in the order of microamps, and it can sensitively be captured only in reverse bias. So, this is something which we should keep in mind. And last is solar cell. A solar cell also functions under reverse bias. So, since it is reverse bias, the current is in this downward direction. I expect you, especially in the last minute preparation, go through all the graphs, practice them once, and go through all the ray diagrams in ray optics chapter. It is very important, practice them, and all the circuit diagrams in semiconductors chapter. It will be very helpful. Thank you.